everyone, so today I'm doing a video on U substitution, which is a technique within integration. Now, for all intents and purposes, you can regard U substitution as a sort of reverse chain rule. So you'll recall from differentiation, if you're differentiating a function inside of a function, what you would want to do is you'd want to take the derivative of the outer function while retaining the inner function and then multiply that by the derivative of the inner function. And that's the form that we're going to see within the integral that's going to prompt us to utilize U substitution. So what we'll want to do here is you want to identify that inner function and set that to be your U. So here we see we're going to set our U to gx, and then we're going to differentiate that U with respect to x to obtain g prime of x. And then on isolating that for d of x, we obtain d of x as a function of du and of g prime of x. What we can then do is we can take that d of x, that dx, and the u itself, and we substitute both equations back into our original, and we'll find that it nicely cancels. So here you see that f is no longer a function of g of x, and since we substituted u as g of x, it's now a function of u. And on substituting our function of du and g prime of x for the dx, we'll find that the g prime of x will actually cancel, and it will usually leave you, if you've done it correctly, as a constant multiple. Okay, so moving on to our first example. We have the integral of x e to the exponent of x squared minus 2. So here you'll see that the inner function is the x squared minus 2, and we'll set that equal to our u. And then on differentiating this u, we're going to obtain the derivative of 2x. So we then want to isolate that for dx, as we mentioned before. And then we want to substitute both equations into our initial and see how it cancels. So here we're left with xe to the exponent of u times du over 2x. And I'm just going to move this over just to make it look a little bit more conspicuous. But you'll see that the x's will indeed cancel and leave you with just a constant of 1/2, which you can nicely move into the front due to the constant multiple rule. And this should make you really happy to see, because we do know how to integrate e to the exponent of u. And so our answer is just going to be e to the exponent of u times 1/2, wherein we'll probably want to resubstitute the initial x equation to obtain the final answer of 1/2 e to the exponent of x squared minus 2 plus c, of course. Yeah, so that's just a really simple demonstration of how you can use U substitution to make something rather complex look a little bit simpler. For our next example, we're going to integrate sine x times e to the exponent of cos x with respect to x. So this brings in some of the trigonometric equations and functions, and we'll recall that if you were to differentiate cos x, you would obtain negative sine x. And that's what indicates that we should be using U substitution, because we see both sine x and cos x in the integral. So because of this, we're going to let our u be cos x, and on differentiation, we are going to obtain what we previously mentioned, negative sine x. So we'll find that once we isolate that for dx, we obtain du over negative sine x, and on substituting both of those small equations into our initial integral, we'll find that the signs will actually cancel. You do want to remember to retain the constant here, which is a -1, and we're going to move that out in front. And once again, we end up with something that makes us rather happy to see, the EU du, because we do know how to integrate that. And it's just going to be -e to the exponent of u plus c, wherein upon resubstituting our x function for the u function, we just get -e to the cos x plus c. So now moving on to something a little bit more complicated, we have the integral, and this time it's a definite integral from 0 to 1 of 2x to the exponent 4 times x to the exponent of 5 plus 2 all to the exponent of 3. Now, because we have a definite integral, there are actually two ways that we can finish this question off, and I'll show that to you later. But what indicates that this is a u substitution once again is that if we were to integrate this u function of x to the exponent of 5 plus 2, we obtain a constant multiple of what we see before that. So once again, we isolate for dx, and we substitute both of these smaller equations into our initial integral. I know we've kind of gone through the same thing a couple of times now, but I really want to reiterate that it's a very systematic approach that you can take on u substitution, and as long as you select the right function to be u, it'll always cancel and work out very nicely. So here we're left with a 2 over 5 in front of our integral as the constant. And of course, we're still integrating from x equals 0 to x equals 1. And now our integral is just u to the exponent of 3 du. So here we want to use the power rule for integrals, and that states that if we have x to the exponent of n, what we get on integration is 1 over n plus 1 times x to the exponent of n plus 1. And here we have our n is 3. So that means once we evaluate this, we're going to get u to the exponent of 4 times 1 over 4. And of course, we're evaluating that from x equals 0 to x equals 1. So this is where you do have two different approaches that you can take. One is we can retain the function u to the exponent of 4 times 1 over 4, and we can substitute u in our bounds. Or, alternatively, instead of keeping our function, we can substitute x in our equation. So I'll show you how to do both of these. Usually it'll be pretty circumstantial, wherein one will give a favorable result in a favorable process. I personally prefer to substitute u in the bounds, because it usually leaves you with a simpler function. But of course, it's personal preference. So for this first technique, you're going to recall that we did set our u to be a function of x. So we can just back substitute x for u and obtain our bounds in terms of u. So here u was equal to x to the exponent of 5 plus 2. So then we'll find that when x is 0, u will be 0 to the exponent of 5 plus 2. Which is just going to leave you with 2. And similarly, when x is 1, u is going to be 1 to the exponent of 5 plus 2, which is going to leave you with 3. And now you'll take those two new bounds, and we're going to apply this function from u equals 2 to u equals 3. And you'll notice I did combine the two fractions, the 1/4 and the 2/5, to make 1/10. So we're left with 1/10
So that is going to leave you with 1/10
the whole
times
of 3 to the exponent of 4 minus 2 to the exponent of 4.
2 to the exponent of 4.
Which is all in all going to leave you with 1/10 times 81 minus 16. And on performing that subtraction, you're going to be left with 1/10 of 65. which is going to leave you with 6.5. So that's the first method that you can use. The second one is to, instead of substituting u in the bounds, you can substitute x in the actual equation. So similarly, we recall that u was equal to x to the exponent of 5 plus 2. So wherein we have 1 over 10 u to the exponent of 4 from x equals 0 to x equals 1, we will then have 1 over 10 times x to the exponent of 5 plus 2, and that to the exponent of 4. So we just nicely substitute our numbers in for x, and we subtract the lower from the upper. And once again, we're going to end up with 3 to the exponent of 4 minus 2 to the exponent of 4 times 1/10, which is still going to give you 6.5. So that's just a good indication that regardless of which method you use, you will get the correct answer. So it's really up to you at that point. So for our last example, we have the integral from 0 to 2 of 2x over the square root of 2x squared plus 1, and with respect to x. So this is similarly u substitution via the same method of pattern recognition, wherein the derivative of 2x squared is going to give you a constant multiple of what we see in the numerator. So we set our u equal to what's inside the square root, which is 2x squared plus 1. And as we mentioned before, our du by dx is going to be 4x. Okay, once again, we substitute these two simple equations, and then we'll find that it nicely cancels because we're going to end up with 2x over 4x, which is just going to cancel to 1/2. So we're just left with 1/2 and the integral of u to the negative 1/2 based on the exponent laws, where we can move something in the bottom up by applying a negative exponent. And once again, we're using that same integration law with respect to powers of x. And here n is negative 1/2. So n plus 1 is going to give positive 1/2. So as a result of that, we have u to the exponent of 1/2 over 1/2. And of course, we're dividing by 1/2 and multiplying by 1/2, so it just simplifies to 1, and we're left with u to the exponent of 1/2. Since this is meant to be taken from x equals 0 to x equals 2, you have the same two options that we had before. So either we substitute u in the bounds, or we substitute x in the actual function. So once again, I'll show you both approaches. You'll quickly find after doing a few of these questions that you might prefer one to the other. So you remember that we set u equal to 2x squared plus 1, and hence on taking our bounds in terms of x, we have x equals 0 to x equals 2, and when x is 0, our u is going to be 1. So when x is 2, our u is going to be 9. So now we're taking this function u to the exponent of 1/2, aka the square root of u, from u equals 1 to u equals 9, and we have nicely root 9 minus root 1, which is going to give you 3 minus 1, or 2. So if we use the second method, Instead of using that u function to find our new boundaries, we're just going to put it straight into the equation. And by that method, we get 2x squared plus 1 to the exponent of 1/2, and from x equals 0 to x equals 2. So then we're going to get 2 times 2 squared, which is 8, plus 1 is going to give you 9, and we're going to take the square root of that, minus 2 times 0 squared plus 1, which is going to give you 1, and the square root of that, which is 1. And you'll see that these are all familiar numbers, so we end up with root 9 minus root 1, which is 2.